Welcome to this talk. I'm Haikun-Ji. I will introduce our work on unsupervised learning-based non-rigid registration for fast motion-compensated coronary MR image reconstruction. I have no financial interest to declare. As we know, whole-heart coronary angiography is important for comprehensive screening of coronary artery disease, and coronary MR angiography is a promising imaging modality without ionizing radiation and contrast injection. However, CMRA is challenging due to the small size and tortuosity of the coronary arteries, and the actual efforts to deal with the respiratory and cardiac motion may result in long acquisition time. Recently, our group have proposed the accelerated free breathing whole-heart CMRA framework. ECG tracking is used to reduce cardiac motion, and an image navigator is acquired in each heartbeat to monitor the respiratory motion in the foot-height and left-right dimension. For the 3D acquisition, a variable density spiral-like profile order is used to enable flexible retrospective binning. And for motion correction, the whole case space is binned into different motion states according to the motion curve estimated from the INAV images. After intra-beam 2D translational motion correction and beam images reconstruction, the intra-beam 3D non-rigid motion is estimated, followed by the motion-compensated reconstruction. However, the whole MOCO framework may be time-consuming, especially the beam-to-beam non-rigid registration step. Here, I'm going to introduce you some details of the non-rigid MOCO reconstruction. In the reconstruction equation, X is the image to be reconstructed at the target motion state. UB is the interpolation matrix transforming X to beam B, and Y is the binned case space. This equation is commonly solved using conjugate gradient algorithm. We can see that both the backward motion, which transforms the moving beam to the reference beam, and the forward motion, which transforms the reference beam to the moving beam, are required to calculate the gradient function. In practice, to reduce the registration complexity, we only measure the backward motion, and the emission transpose of the backward transformation is usually used to approximate the forward transformation. However, there is no guarantee that the backward motion is invertible. Instead, the diffeomorphic registration method can be used. It generates a series of time-dependent velocity fields, from which the invertible motion fields can be obtained. However, the registration time may be further increased with the diffeomorphic registration. So in this study, we aim to propose a learning-based diffeomorphic registration for efficient beam-to-beam respiratory motion estimation. And the beam image reconstruction and the non-rigid MOCO reconstruction can also be implemented using TensorFlow. Then the whole framework can be run on GPU. And the 3D MOCO CMRA reconstruction can be completed in a few seconds. Here shows the diffeomorphic registration network. The input is the 3D beam images, and the output is the velocity fields between adjacent beams, which are inputted to the scaling and screening layer to get the motion fields. The spatial transformation network is used to warp the moving beam images with the estimated motion fields. No motion ground truth is required to train the network. Instead, we measure the image similarity between the warped moving beam images and the reference beam, and the smoothness of the velocity fields. Here shows the unsupervised loss function. In this study, we use the local normalized cross correlation to measure the image similarity, and we take beam 2, which is the motion state close to the end expiration position as the reference beam. For CMRA acquisition, we used a previously proposed free breathing T2 prepared balanced SLP technique. The speed resolution is 1.2 mm with accident factor between 2 to 3. We recruited 20 subjects from clinical acquisitions, and used 12 subjects to train the network. To fit the GPU memory size, we randomly sliced along the fully sampled readout dimension with size of 64, and the batch size is 1. For testing, the network was used to predict the beam-to-beam respiratory motion for 8 subjects, and the motion-compensated reconstruction was compared with a state-of-the-art registration method called NIFTY-REG. We trained the network with 8,000 iterations, and the recorded training loss and test loss shows the convergence of the network. Here shows example beam-to-beam respiratory motion. With the network, we can get both the backward and forward motion. With NIFTY-REG, we only measured the backward motion. Here shows the motion-compensated CMRA images for a test subject, with the motion estimated by the network and NIFTY-REG in comparison with the one without interbeam motion correction. And here shows the reformatted coronary arteries for this subject. We can see that the learning-based method achieved similar image quality to NIFTY-REG and is better than the one without interbeam motion correction. However, with the learning-based method, the whole framework took about 20 seconds, while using NIFTY-REG, only the registration step took about 80 minutes. Here shows the MOCO CMRA images and the reformatted coronary arteries for another test subject. The RESP measurement net achieved similar motion correction performance to NIFTY-REG. Here shows the reformatted coronary arteries for another 2 test subjects. We can see that in subject 1, the RESP measurement net achieves better motion combination in the distal segment of the right coronary artery than NIFTY-REG. So, in summary, we have proposed the unsupervised learning-based diffeomorphic registration for beam-to-beam respiratory motion estimation. It reduced the 3D MOCO CMRA reconstruction to a few seconds, and achieved similar or even better MOCO CMRA quality to a commonly used registration method. No motion ground truth is required during training, so it is possible to perform online learning to update the network weights with newly acquired data. And this method holds great potential for clinical application. For the next step, we intend to train a general respiratory motion estimation network for all kinds of animal-based acquisitions with different contrasts or anatomies. Thanks for your attention.